This example comes out of section 1.6, infinite sequences. First thing I want to talk about, since the title here is infinite sequences, is what is a sequence. The next section that we'll get into in 1.7 is called infinite series. So the difference between a sequence and a series is pretty important. And so if I have a list of numbers like 2, 4, 6, 8, etc., or 5, 10, 20, 40, or even 1, 2, 3, 4. Maybe they're negative, -1, -2, -3, -4. Any list of numbers is a sequence. They may follow, as these ones do, a really predictable pattern and be arithmetic, adding 2 every time, or multiplying by 2 every time, or subtracting 1 every time, but it's a list of numbers. A series is when you start to add those numbers up. So if I say 5 plus 10 plus 20 plus 40, then we're talking about adding numbers up, and then we're talking about series, and we'll get into that in the next section, what happens when we add things up. But for this one, we're just going to talk about terms in a sequence, and what's the next term in a sequence, and general terms of a sequence, and limits of sequences. So let's have the first example. So we're asked in this case to list the first 5 terms in the sequence defined by Tn equals n plus 1 over n plus 2. So if I asked you what term 1 is, you just put 1 into there and you say, well, 1 plus 1 over 1 plus 2 is 2/3. If I asked you what term 2 is, you do the same thing and you'd say, well, it's 3 over 4. Next term is 3 plus 1 over 3 plus 2, so 4 over 5. Term 4, 5 over 6, and term 5, 6 over 7. Really what we're getting to, and why this thing is called infinite sequences, the title of this, is we're going to say, well, what's the limit as n goes to infinity of that n plus 1 over n plus 2. So as I put in more larger and larger numbers, 10, 20, 30, 40, 40 million, 500 trillion, whatever, what you'll see is that you'll always have a denominator that's just one number higher than the numerator. If you look at that graphically, if I look at these numbers here, I've got, if this is 1, I've got 2/3, 3/4, 4/5, 5/6, etc. You're just getting closer and closer and closer to 1. So the statement then could be said, limit as n goes to infinity of n plus 1 over n plus 2 is equal to 1. You can again see that graphically as these points get closer and closer and closer to 1. And you could make them as close to 1 as you wanted just by putting in a value as big as you wanted. If I put in 1,000,000 for n, term 1,000,000 of that sequence is going to be 1,000,001 over 1,000,002, 0.9999. You can make it 0.999999999 by putting in big enough numbers. Next infinite sequence asks us to find the limit as n goes to infinity of 1 over n. So if I looked at the terms here, the first term would be 1, the next one would be 1 over 2, 1 over 3, 1 over 4, 1 over 5, etc. Looking at those again graphically, if I draw a little picture, I've got 1, 1/2, 1/3, 1/4, 1/5. And these numbers do get smaller and smaller and smaller, but they don't decrease without bound. They basically are heading closer and closer to 0. And again, by putting in bigger and bigger and bigger numbers, I could make this approach as close to 0 as I wanted. 1 over 1,000,000, 1 over 1,000,000,000, 1 over, 1 with 100 zeros after it, and you'd have 0.00000000 as far as you want to go. It turns out that in general, even if you had an exponent there, like if I had the limit as n goes to infinity of 1 over n squared, or 1 over n cubed, 1 over n to the 4, that you'd get the same answer of 0, which is a pretty handy fact. The fact that limit as n goes to infinity of 1 over n to the power of anything, I'll put r here, is equal to 0 as long as r is positive, as long as you've got a positive exponent there, is a useful tool in solving some kind of more complicated limits that we'll run into in the next example.